So today I want to talk about Euler's method. Euler's method is a way to solve differential equations, and it's not actually just solving differential equations, but we're actually approximating the value of differential equations. So if we have a curve like this here, we can see that initially before calculus was fully invented, and before we had differentiation, the way to actually approximate this would be draw that tangent line. We already knew how to do that. But that tangent line, the further away you get, you're going to have an error here, right? So if I'm on this tangent line, I don't actually know the slope at this point. I know the slope here at my tangent line. I've got an error. So Euler developed a method where you draw closer and closer and closer tangent lines that are broken up by sections in order to be able to get an approximation of the derivative at a particular point. So let's actually go through an example and you can see this in action. We're asked to show that Euler's method for dy over dx equals 0.5 times x plus y. This is equal to m, this entire derivative here, or differential equation, excuse me, starting at 0.2, 1.11, and using two steps with delta x equals 0.5. We're asked to show that that gives y is approximately 1.775 when x is equal to 0.3. Well, first we're going to start with 0.2 and 1.11. And we're going to use two steps of delta x equals 0.5. So my second step is going to be 0.25 and my third step will be 0.3. Right? So then I'm going to calculate m, which is dy over dx, using this formula that was given. And when I use these 2 points and this formula, I get 0.655. Now, I need to use delta y, or I need to find delta y. I highly recommend using this chart with the x, y, m, delta y, which is equal to m times delta x, and y sub nu, which is equal to y plus delta y, because I think this will make things much easier. Is it frozen? I think this will make things much easier and clearer when you're actually calculating Euler's method. So we find delta y, which is equal to m, which is this value here, times delta x, which is 0.5. I like to write my delta x right above, just so I remember it. And I add this number to my original y to get my y sub nu. I then take this y sub nu and move it here. And I repeat the process, but now I'm using 0.25 and 1.14275. So I get my m, I multiply my m times 0.5, I get this. My delta y, I add delta y to this y, and I get this number here, which I pull down, and there, I found it. When x is equal to 0.3, y is approximately 1.17756. 875, I kind of went out a little bit further, but this is approximately this, so we've done it. We've actually shown that this works. Okay, let's do one more example. We're asked to approximate 4 points on the solution curve to dy dx equals negative 3x squared y, starting at 0, 2 and using delta x equals 0.1. Well, if I start at 0, 2 and I have 4 points with my delta x, I'm going to have 0.1, 0.2, 0.3, and 0.4. Okay, so I can approximate 4 points. Then I'm going to find my m, this time using this differential equation. So your differential equation will likely be provided and different every time. So I calculate m, I take m times delta x, which again is 0.1, and then I add this value to y, I get y sub nu. I carry y sub nu over here. So it looks like 0 and 0.1 are approximately the same. I repeat the process. I find m, I take m times delta x, I add delta y to y, I get this. I move 1.994. I use x and y to calculate m. I take m times delta x. I take delta y plus y, and I get my y sub nu. I move y sub nu again, use x and y, calculate m, take m times delta x, take delta y plus a y, I get y sub nu. And that's my final approximation after moving those. So it's really not too complicated. It's kind of fun to do. Just make sure that you're very careful about the process and that you don't miss any steps. So that's how Euler's method works. Euler was born in Switzerland, a very interesting mathematician, excuse me. So hopefully this helped you, and if you have questions, leave them in the comments and I'll see you in class. Bye.